Recording in progress.
Okay, so we're now going to move from sequences to infinite series. And if we thought of sequences as functions on n, functions of n, this is a1, this is a2, this is a3, and so on. This is n equals 1, n equals 2, n equals 3, then what a series represents is like the area under the curve. So an can be thought of as like f of x, and something that we're going to call an infinite series, which is the sum starting at n equals 1 to infinity. We're going to think of that as like the integral from 1 to infinity of f of x. And what this means here is it means a1 plus a2 plus a3. And you just add all the terms in the sequence. And really, what it really, because infinity is not a thing, there's actually just a limit as a capital N goes to infinity of something called a partial sum. So this is called a finite or a partial sum. So if the limit exists, the series is called convergent. If not, or the limit does not exist, the series is called divergent. Okay, so that is the basic tool that we'll be using for the next few weeks, because it really has quite a bit of utility in applications. And we'll get to some of those later. Right now, we just need to build up some examples and some groundwork. So let's just talk about a few examples of series first. So I think here's the simplest series you could write down. I'm just going to sum the number 1. So what this actually is, it's the limit of this finite sum, which just means add up 1 n times. So this is equal to 1 plus 1 plus 1. And this is overall n times. So it's just equal to n. So in other words, this is the limit of n. And the fact that this area is infinite should not be any surprise. And this is actually, we're free to think of series as area, right? Because let me just write down again what a sequence looks like. We can think of it as a function on integers. And so the thing is that if I wrote down the area under this curve, the rectangles, they all have boxes, they all have lengths of width 1. So actually, this area is just a1 times 1. So the total area is a1 times 1 plus a2 times 2 plus a3 times 3, and so on. This is equal to our series that we just defined. So it is series is equal to area under the sequence. Anyways, so how about we consider another example of the series? That one was divergent. So another example, you could consider this series where an equals 0 for n larger than 10, for example. And so this series is actually is definitely convergent because it stops counting after 10 times. After this, so if this is 10, for example, then the area is just 0 afterwards. So the limit, as capital N goes to infinity, it's actually just equal to the series up till n. And the reason I bring up this kind of silly looking example is because we can think of this having a very steep tail. So this example kind of looked like this. So the tail vanishes quickly. For convergence series. So in other words, an should go to 0 as n goes to infinity. And it should do so quickly in some sense. So, and we'll have to figure out how quickly. So just looking ahead, an, this is the borderline case. So if you have series that, like the previous one, which converge very quickly, then you also have divergence series like 1. So you can think of this as 1 over n to the infinity, and you can think of this as 1 over n to the 0. Then it shouldn't be a surprise that there's a borderline case 1 over n to the 1 over n to some power. It turns out the power that's borderline here is 1. And so if you go above this, it's a divergent. And if you go below this, it is actually convergent. And we'll get to that momentarily. For now, how about we give another important example of a series? And I hope you will join me for the next video where I discuss this. Thank you for watching.